Now we're going to look at some applications of the natural exponential function, the exponential function with base e, and we're going to start with an application that we teased last time. In the previous lecture, we looked at the scenario where we invest $1 at 100% interest compounded n times per year for 1 year, and we investigated what would happen as we let n get larger and larger and larger. We saw this number e kind of pop out of that naturally. Well, we're going to generalize that idea. Rather than looking at the case of investing $1 at 100% interest for 1 year, let's just take the general formula, P dollars invested at interest rate R for T years. And we're going to ask what happens as n goes to infinity. Well, you can prove that as n goes to infinity, the compound interest formula becomes P times e to the RT. You can see in particular that if P, R, and T were all 1, then the answer would be E, which was the example that we did last time. Now we've generalized this for any sum of money at any interest rate for any time period. Let's write this up a little more formally. If a sum of money P is invested at an interest rate compounded continuously for T years, then the balance A is given by A equals PE to the RT. The way that we describe in words that we're letting the number of compounding periods go to infinity is we say that the interest is compounded continuously or instantaneously. So there aren't a finite number of compounding periods. The interest is being compounded continuously. Well, this formula says that if you compound the interest continuously, then the amount of money you'll have is given by this exponential expression, PE to the RT. Let's do an example of this. If $500 is invested at 3% compounded continuously, find the value of the investment after 15 years. We're looking for the balance of an investment where the interest is compounded, and now we have two formulas. We have the P times 1 plus R over N to the NT formula, and we have this new PE to the RT formula. The way that you can tell which formula you're supposed to use is based on how often the interest is compounded. If the interest is compounded a finite number of times, 1 time per year, 2 times per year, 4, 12, 365, then you use the formula with the n in it, because that's the number of compounding periods per year. But if the interest is compounded continuously, you want to use this new formula, which I sometimes call the PERT formula, because the symbols in the formula spell the word PERT. So we're going to use the PERT formula here. A equals PE to the RT. A is the question, what is the value of the investment? P is $500 because we're starting at 500 bucks. R is 0.03 for 3%. T is 15. You might ask why I didn't list E. Remember, E is not a variable. E is a number. It's around 2.7. I don't need a substitution for E because E is already a constant. Don't put that in your list. You don't substitute anything in for E. It's a number. Plugging our numbers in, we get A equals 500 times E to the 0.03 times 15, and now we just have to put that into the calculator. 500. You can raise E to a power by pushing second and this ln key, and then I can just put the arithmetic inside the parentheses, 0.03 times 15. You can also simplify that to 0.45 first. Hit enter. And we get about $784.16. Let's look at an example a little bit different than anything we've done so far. This says how much money must be invested now at 5% compounded continuously in order to reach a balance of $2,500,000 in 35 years. Well, we can see the interest is compounded continuously, so we're going to use that PERT formula again. What makes this problem different than anything that we've done previously is that we're not looking for the balance. We know the balance. The balance is $2.5 million. The question is, how much do you start with? What is the principal? The interest rate is 5%, 0.05. The time is 35 years. And we want to know what lump sum we have to set down in order to reach this $2.5 million. So we get the equation 2,500,000 equals P times E to the 0.05 times 35. And we have to solve this for P. Keeping in mind that this is implied multiplication, that algebra isn't difficult. We're going to divide both sides by E to the 0.05 times 35. So the exact value of P from this equation is 2,500,000 divided by e to the 0.05 times 35. But this is a practical problem, so we're going to give an estimate for the answer. If you went to your financial advisor and they said you have to invest 2,500,000 divided by e to the 0.05 times 35, you'd be like, what are you talking about, dork? Just tell me how much money. So let's round this off. 2,500,000, that's 5 zeros after the 25, divided by e to the 0.05 times 35. So we need to start with $434,434.86. That's a lot of money to put into a lump sum investment. We're probably going to have to use another investment strategy to reach our goal. Instead of using a lump sum, we might have to invest slowly using an annuity or something like that. Now, these two examples were about the continuous growth of the balance of an account. We can generalize that to any quantity. Let Q sub 0 be the value of a quantity Q at time equals 0. If Q changes instantaneously at a rate proportional to its current value, then Q equals Q sub 0 e to the RT. I want you to notice that this is just the PERT formula, but with Q in place of A and Q sub 0 in place of P. This is really the same formula. It also allows for something that decreases. Notice that we're just saying that Q is changing instantaneously at a rate proportional to its current value. So if Q is increasing over time, then we'll have a positive rate like we saw in the money examples. But if Q is decreasing over time, then R is less than 0. We'll have a negative rate, and that's what we refer to as exponential decay. We'll look at examples of both. In this example, instead of talking about money, we're going to talk about squirrels. A population of squirrels is rapidly increasing in a certain neighborhood. The current estimate is that there are 200 squirrels present and that the population is growing continuously at a rate of 30%. Assuming this growth rate holds, predict the number of squirrels in the neighborhood 6 years from now. Notice that we're told that the population is growing continuously at some rate. This is what we call exponential growth. The model for exponential growth is Q equals Q sub 0 e to the RT. Q is the number of squirrels at the end of the time period, and that's the question. Q sub 0 is the number of squirrels we started with. That's what the sub 0 is supposed to indicate, that it's the number of squirrels or just the quantity in general at time 0. This is 200. The growth rate is 30%, that's 0.3. T is 6. And so now we can plug these into the formula. Q equals 200 e to the 0.3 times 6. And we can just throw that into the calculator. 200 e to the 0.3 times 6. And we have over 1,200 squirrels. It's 1,209, 1,210. Over 6 times what we started with. Let's look at another example. A previously unknown YouTube creator has a video which is beginning to pick up steam. It stands at 40,000 views now, and the views are increasing continuously at the rate of 15% per day. If we assume the growth rate holds steady over the next month, how many views will the video have 30 days from now? Notice that it says that the views are increasing continuously. That's our key that we're going to use this exponential growth formula. Q equals Q sub 0 e to the RT. I'd like you to try to fill in the unknown quantities here and come up with this prediction. Q is the question. Q sub 0 is the number of views we started at, which is 40,000. E is a constant. Don't plug anything in for E. We're going to use the calculator for that. That's not a variable. That's just a number. It's around 2.7. R is 0.15. T is 30. The rate is 15% per day, so the variable T is being measured in days. So T is 30. So we get that Q is equal to 40,000 times e to the 0.15 times 30 power. We're just going to approximate that with the calculator. 40,000 times e to the 0.15 times 30. After 30 days, this will have grown to just over 3.6 million views. That's how I'm going to round this. Let's do an example with decay. This says, a radiopharmaceutical is used for medical imaging of the lungs. When a sample is created, it begins to decrease at a rate of 11.5% per hour due to radioactive decay. If 100 units are initially available, how many units will be remaining in 2 hours? So this radioactive isotope is injected into the body so that you can do this imaging. But because it's radioactive, it decays away. And so when this radiopharmaceutical is created, it immediately starts to decrease in size. That decay is happening at an instantaneous rate, and so we want to use that same formula, Q equals Q sub 0 e to the RT. The question is how many units will be remaining in 2 hours. That's the Q. How much will be left over? Q sub 0 is the amount we started with. We're starting with 100 units. R we need to be careful about. Let me go back to our formula here. Because Q is decreasing over time, we want to use a negative value for R. R is less than 0 in an exponential decay model. We're going to convert 11.5% to its decimal value of 0.115, but we're going to use the negation of that number to indicate exponential decay instead of growth. T, the time is in 2 hours, but the rate is also in hours, so we're going to use T equals 2. This again just becomes plug and chug in your calculator. This is 100 e to the negative 0.115 times 2. We'll approximate that with the calculator to get the number of units after 2 hours. 100 e to the negative 0.115 times 2 comes out to about 79.5 units. So if 100 units are initially available, after 2 hours you'll only have 80 units left over. So let's flip the question a little bit. Suppose you need 100 units at the end. Then you can't create 100 units because just in the transfer over to the patient, you're going to lose a little bit. So let's answer that question. A radiopharmaceutical is used for medical imaging of the lungs. When a sample is created, it begins to decrease at a rate of 11.5% per hour due to radioactive decay. If we need to be sure that 100 units will be available 1 hour from now, how many units should be created? We're going to have to create more than 100 units because it's decaying away. We know the model for exponential decay is Q equals Q sub 0 e to the RT, but now Q is 100, that's what we need to end with, and the initial amount is the question. R is still negative 0.115, we're using the negative because of the radioactive decay. The amount is decreasing over time. T is only 1 this time. Plugging in our numbers, we get 100 equals Q sub 0 e to the negative 0.115 times 1. We transfer this to another slide. To solve for Q sub 0, remember that this is implied multiplication, so we're going to divide by the exponential expression. And so Q sub 0 is equal to 100 divided by e to the negative 0.115. Multiplying by 1 doesn't change the exponent. But let's turn this into a practical number that we can understand. 100 divided by e to the negative 0.115. I want you to think about whether this answer should be bigger or smaller than 100. Of course it should be bigger because it's going to decay down to 100. So we have about 112.2 units. You want to make sure you round up here. We don't want to round this down to 112 because if we start with 112 units, we're going to decay below 100. You're definitely going to want to find some more examples for exponential growth and decay. Make sure you take a peek at some money examples, but also do some things that aren't money, the more general formula. If you have any questions for me about the examples that I did in this video or examples that you find in a textbook, let me know. We can talk about it during an office hour or we can shoot some emails back and forth.